Somewhere above the Chilean Andes, at this exact moment, a camera the size of a small car is taking a new photograph of the night sky. It just finished one. It's already taking the next one. 40 seconds, and it happens again, all night, every clear night, for the next 10 years. And in the 6 weeks before that camera officially started its real mission, it had already found more than 11,000 objects in our own solar system that no human being had ever seen before. Some of them close enough to Earth that they qualify as near-Earth asteroids. That's what we're unpacking today. If you're new here, this channel breaks down real space missions and real scientific data, no guesswork, no invented drama. So if that sounds like your thing, go ahead and subscribe before we dig in. To understand why this matters, you need to know what this telescope actually is, because it isn't just another big mirror pointed at the sky. It's called the Vera Rubin Observatory, jointly funded by the U.S. National Science Foundation and the Department of Energy, built at a cost of roughly $800 million. And it sits at the summit of Cerro Pachon in northern Chile, at an elevation of about 2,682 meters, chosen specifically because the air there is dry and the skies are dark almost every night of the year. It shares that mountaintop with two other well-established facilities, the Gemini South Telescope and the SOAR Telescope, which gives you a sense of just how prized that particular patch of sky already was before Rubin arrived. The observatory is named after Vera Rubin, the American astronomer whose observations of galaxy rotation in the 1970s provided some of the strongest early evidence that dark matter exists, a discovery she never received a Nobel Prize for, despite how foundational it turned out to be. The facility was formally renamed in her honor in January 2020, and it carries her name specifically because its central mission is to chase the two biggest open questions she helped create: what dark matter actually is, and what dark energy is doing to the expansion of the universe. The project's roots go back further than most people realize. Discussions among astronomers about a survey telescope like this began in the 1990s, and the concept gained real momentum in 2007, when Seattle area technology figure Charles Simonyi and Microsoft co-founder Bill Gates jointly contributed $30 million toward early construction, which is why the telescope itself carries a second name, the Simonyi Survey Telescope, distinct from the observatory as a whole. Formal construction on the mirror began that same year using private funds. The project was ranked as the top large ground-based priority in the 2010 Astrophysics Decadal Survey, and full construction of the facility officially began on August 1st, 2014. At the heart of the finished observatory is an 4-meter mirror system using an unusual 3-mirror design that lets the telescope swing from one point in the sky to another far faster than a conventional observatory of similar size, feeding light into the LSST camera, a 3,200 megapixel instrument built from 189 individual sensors, weighing about 3 metric tons, and officially the largest digital camera ever constructed for astronomy. Each single image it takes covers 6 square degrees of sky, an area equivalent to roughly 45 full moons side by side, and every one of those images would need about 400 separate 4K television screens just to display at full resolution. Getting that camera into place wasn't simple. The instrument recorded its first engineering pixel in October 2024, and even after that milestone, the project wasn't finished troubleshooting. In the weeks before the public unveiling, engineers were still dealing with the camera itself overheating inside the dome, a problem serious enough that Sky and Telescope reported scientists working late into the night that May, running diagnostics and fixes just to keep the schedule on track. That kind of last-minute technical fire drill is normal for a project this ambitious, but it's worth mentioning because it's easy to watch a polished announcement video and forget how much unglamorous troubleshooting sits behind it. That work paid off. On June 23rd, 2025, the observatory released its so-called first look images based on roughly 10 hours of test observations, and those first images alone told you what this instrument was capable of. One release combined 678 individual exposures, totaling a little over 7 hours of observing time, into a single composite image of the Trifid Nebula and the Lagoon Nebula, both several thousand light years away, revealing gas and dust structures too faint to appear in any single shorter exposure. A second release, built from more than 1,100 overlapping images, captured a section of the Virgo galaxy cluster containing roughly 10 million galaxies, and astronomers were careful to point out that figure represents only about 0.05% of the nearly 20 billion galaxies the observatory expects to catalog over its full 10-year mission. But the detail that actually made headlines wasn't the nebulas or the galaxies. It was what the telescope found moving. In those same 10 hours of test observations, Rubin detected 2,104 previously unknown asteroids in our own solar system, including 7 near-Earth asteroids, all of which NASA and the observatory team confirmed posed no danger. For comparison, all other ground and space-based observatories combined discover roughly 20,000 new asteroids in an entire year. This one telescope found over 2,000 in less than half a day of test observing, before its real survey had even begun. That gap between what existing observatories can find and what Rubin can find isn't a small improvement. It's a difference in kind, and it comes down to a combination the observatory was specifically engineered around. An enormous field of view, extremely high sensitivity to faint, fast-moving light, and a cadence fast enough to photograph the same patch of sky repeatedly within the same night. Most asteroid surveys have to choose between depth and speed. Rubin was built to do both at once, which is why its first taste of real operation immediately outpaced systems that have been running for years, and it's also why researchers involved with the project have said plainly that Rubin is expected to discover more asteroids in its first year of full operation than humanity has cataloged across the previous 400 years of astronomy combined. Right now, astronomers have identified roughly 1 million asteroids across the entire solar system. Current estimates suggest tens of millions actually exist within reach of ground-based detection. Closing that gap, safely and systematically, is a huge part of why this telescope was built in the first place. After that first look event, the observatory didn't launch straight into its 10-year survey. Instead, it moved through a formal transition to operations on October 25, 2025, followed by months of further calibration and system optimization. On February 24, 2026, the team activated what they call the Real-Time Discovery Alert System, the pipeline responsible for automatically flagging anything in the sky that changes, brightens, dims, or moves between exposures. On its very first night running at full capacity, that alert system generated roughly 800,000 individual notifications, each one a potential asteroid, supernova, flaring galaxy core, or variable star worth a second look, sorted automatically and pushed out through independent software systems called alert brokers, which distribute the flagged events to astronomers around the world within roughly a minute of the data being captured, so that other telescopes can follow up while a fast-fading event is still happening. Then, on June 30th, 2026, the observatory reached the milestone the entire project had been building toward for more than 2 decades, the official start of the Legacy Survey of Space and Time, known as the LSST, a 10-year campaign to photograph the entire visible southern sky in 6 different filters, roughly 825 times per patch of sky, every 3 to 4 nights, without stopping. NSF director Brian Stone described the moment simply, saying the observatory was beginning to film the greatest cosmic movie ever made. During the roughly 6 weeks of optimization observing that led up to that official start, before the survey had even formally begun, Rubin had already discovered more than 11,000 previously unknown asteroids, including 33 near-Earth objects and 380 trans-Neptunian objects, small bodies orbiting out past Neptune in the solar system's outer reaches. None of those objects represent a known threat. What they represent is proof of a detection rate nobody has managed before, at a stage when the telescope was still technically warming up. Now that the full survey is underway, that detection engine runs every single night. The camera captures a fresh, full-resolution image approximately every 40 seconds. Across a typical night, the observatory generates around 10 terabytes of raw data and produces as many as 7 million individual alerts, flagging something that changed since the last time that patch of sky was photographed. To put that data volume in context, the observatory's own team has stated that in its first year of operation alone, Rubin will collect more astronomical data than every other optical observatory on Earth combined, historically put together. Over the full 10-year survey, the observatory's own project documentation describes a final data product spanning several hundred petabytes, once every processed image, catalog, and reprocessing pass is included, cataloging an estimated 17 billion stars and 20 billion galaxies, along with millions of asteroids, comets, supernovae, and other transient events, all of it made publicly accessible through an online portal called the Rubin Science Platform, so that any astronomer with an internet connection, not just those with access to a major telescope, can search the data directly. That scale of automated nightly detection is where the honest version of this story gets genuinely significant, without needing to exaggerate anything. Rubin's most immediate practical value isn't abstract cosmology, it's planetary defense, one of the observatory's 4 formally defined science goals, alongside probing dark matter and dark energy, mapping the structure of the Milky Way, and exploring the transient optical sky. On the solar system side specifically, the mission's own stated aim is to build as complete an inventory as possible of smaller bodies out there, especially the potentially hazardous asteroids that could someday come close to Earth. Internal simulations suggest the survey could ultimately map several million asteroids over its 10-year run, the overwhelming majority of them harmless main belt objects, but including a meaningful fraction of near-Earth objects that current surveys haven't found yet, simply because they're too faint or too fast for existing telescopes to catch. Finding those objects early, cataloging their orbits, and tracking how those orbits evolve over years is exactly the kind of unglamorous, methodical work that turns a potential surprise into a known, trackable non-emergency. NASA and other agencies have spent decades trying to complete the catalog of near-Earth objects large enough to cause serious damage, and Rubin's detection rate in its first weeks alone suggests it will meaningfully accelerate that effort, not by discovering something we should panic about, but by closing gaps in a catalog that has always had gaps. The Milky Way mapping goal works on a similar logic, just turned inward instead of outward. By repeatedly imaging billions of individual stars across the galaxy and stacking those observations over 10 years, Rubin is expected to reveal extremely faint stellar streams, the scattered remains of smaller galaxies that the Milky Way pulled apart and absorbed over billions of years of gravitational interaction. Those streams already exist in the sky right now, but they're too faint and too spread out for most existing surveys to trace clearly. A telescope built to photograph the same enormous patches of sky hundreds of times over a decade is exactly the kind of instrument that can finally pull that faint structure out of the noise, giving astronomers a clearer fossil record of how our own galaxy actually grew. Beyond the solar system and the Milky Way, Rubin's core scientific purpose is aimed squarely at dark matter and dark energy, the two problems tied most directly to Vera Rubin's own legacy. The observatory's highest priority science goal in that category is something called weak gravitational lensing. The subtle, almost imperceptible distortion in the shapes of distant background galaxies caused by the gravity of unseen mass, including dark matter, sitting between those galaxies and us. By measuring that distortion across billions of galaxies rather than thousands, Rubin is expected to produce the most detailed three-dimensional map of the universe's mass distribution ever assembled, providing an independent, high-precision test of whether dark energy behaves as a fixed cosmological constant. The assumption most cosmology has been built on, or whether it has actually changed over the history of the universe. That question isn't settled. Earlier in 2026, a separate survey called the Dark Energy Spectroscopic Instrument, DESI, completed its own multi-year mapping campaign and reported results hinting that dark energy might not be constant after all. Rubin's data is specifically designed to test that hint independently, using a completely different method involving supernova photometry and galaxy distribution alongside the lensing measurements, which is exactly how science is supposed to confirm or rule out a surprising result rather than take it on faith. The fourth pillar, exploring the transient optical sky, is really about catching things that happen fast and don't wait around for a scheduled observation. Novae, supernovae, gamma-ray bursts, quasar variability, and other short-lived flares in brightness have historically been caught mostly by luck, whichever telescope happened to be pointed in the right direction at the right moment. Rubin's rapid, repeated cadence across the entire visible sky changes that math substantially, because instead of hoping to catch an event by chance, the survey is simply watching everywhere, constantly, and letting its alert system flag anything that changes the moment it happens. That's part of what enables what astronomers call multi-messenger astronomy, cross-referencing an optical flash from Rubin against a gravitational wave detection or burst of high-energy particles recorded by a completely different instrument to build a fuller picture of a single violent cosmic event from multiple independent angles. None of this means Rubin has already rewritten cosmology, and it hasn't found anything that threatens Earth. What it has done, concretely, is start operating at a scale of detection that simply didn't exist before June 2026. An automated system finding thousands of new solar system objects and millions of changing points of light every single night, feeding a decade-long data set that will let astronomers everywhere, not just a handful of institutions with their own telescopes, dig through the same raw material and look for whatever it turns up. As of this recording, the observatory has already scheduled its next public data milestones. An early data preview called EDP2 is set for release on July 27, 2026. A larger data preview, DP2, is expected sometime between October and December of 2026. The first full formal data release, DR1, isn't expected until roughly 2 years after the survey's official start, meaning sometime in mid to late 2028, once enough repeated observations have accumulated to produce the deep, stacked imagery the survey depends on for its faintest detections. In the meantime, the nightly alert stream keeps running, and anyone can follow real-time status updates directly through the observatory's own website and its public alert dashboard. What remains genuinely unknown is, in a sense, the entire point of the mission. Nobody, including the scientists who built it, can tell you in advance what Rubin's 10-year time-lapse of the sky will eventually reveal. Some of what it finds will be expected. More asteroids than any survey before it, more supernovae caught earlier in their explosion, a sharper picture of how dark matter is distributed across the cosmos, and a direct, independent test of whether dark energy has been changing over cosmic time. But observatory leadership has also been explicit that part of the reason a survey like this runs for a full decade rather than a single season, is to catch the events that are slow, rare, or simply never predicted. The kind of astronomical phenomenon that has never been systematically observed before because no instrument has ever watched the entire sky, every few nights, continuously for that long. Deputy Director Phil Marshall put it plainly when the survey began. Millions of alerts in just the last couple of months already prove the Discovery machine works. What that machine will eventually surface, across 10 years and hundreds of petabytes of accumulated data, genuinely hasn't happened yet. So the honest way to end this isn't with a warning, it's with a simple fact. Somewhere over Cerro Pachon right now, that camera is still running, still taking a new photograph roughly every 40 seconds, still quietly building, one exposure at a time, toward a picture of the universe more complete than anything that's existed before it. And nobody, not the astronomers, not the engineers, not the software running the alerts, actually knows everything that picture is going to contain until it's already been taken. If this kind of deep dive into real current space science is what you're here for, subscribe so you don't miss the next one, drop a comment with what you want covered, and share this with someone who'd want to know what's actually happening on that mountain in Chile right now.